So as you can see in the first slide, we are going to be talking about the most massive planets in the solar system. We call them the gas giants because composition-wise, Jupiter and Saturn being much more larger than the Earth, they are basically composed of 71% hydrogen, 24% helium, and 5% of other elements, other gases, like, for example, ammonia. Both planets have a higher percentage of heavier elements than the sun, for example, right? The sun, when we look at the sun, when we look at the spectrum of the sun, we see mostly hydrogen and helium. In the case of Jupiter and Saturn, we also see mostly hydrogen and helium, but we see a higher percentage of heavier elements. So that's a good detail to emphasize and highlight when we look at the difference between these planets and the sun. We have launched several missions to explore Jupiter and Saturn. The Voyager 1 and 2 are the ones that people should know the most. They were launched in the late 70s. But we have also launched the Juno mission recently in the 2000s. And in 1989, we launched the Galileo spacecraft, which arrived to Jupiter in 1995 and ended its exploration of Jupiter in September 2003. And these missions, the main idea or the relevance of these missions is to be like flybys orbiting Jupiter, taking pictures and exploring the atmosphere of these planets. In the case of this mission in particular, I believe to finish the mission, they made it crash into the atmosphere of Jupiter. And they did this with the idea to explore at least the upper layers of the atmosphere. You probably have watched or have heard what would happen if you try to land on a gas giant. First of all, there is no surface, right? Where the mantle of the planet should be. And when I mean about when I refer about the mantle, I'm talking about the same layer that we have here on Earth. We have the crust, and then we have the huge mantle between the crust and the core. So instead of a mantle, we find layers of clouds of different compositions inside Jupiter and Saturn. So the idea of crashing a mission like Galileo, as it's finishing its lifetime, exploring the planet and the moons as well, is to actually take some information and gather some data that can be sent to the Earth to give us more insights of the characteristics of at least the surface of these clouds, right? By exploring Jupiter, the composition of Jupiter, the orbit of Jupiter, we have concluded that Jupiter most likely has a rocky core several times more massive than the Earth. The core is surrounded by liquid ices, and these are not really just water. This can be ammonia, methane, and other compounds. On top of this layer, that's where we find helium and liquid metallic hydrogen. That will be in what we will know as the mantle of the Earth, right? That will be the mantle of Jupiter. And the outermost layer of this planet is mainly composed of hydrogen and helium gas. And we have different belts. And we know this because of the different colors, as you can see here or even here, right? These are the belts that we see in Jupiter, more noticeable than Saturn, even though Saturn also has those. We're still not sure why these colors and why the composition is like this. We know it's like that because of the different compounds at the different altitudes that we can find. And as we explore the atmosphere of Jupiter and Saturn, you will see the different composition of the layers of the atmosphere of Jupiter and Saturn. However, it's still not very well known what creates this different coloring in the belts of the clouds of Jupiter and Saturn. So the idea with this chapter is at least to answer some of the observations and what has been revealed about Jupiter and Saturn, the nature of the storms that we can see in the clouds, for example, the red dot of Jupiter, what the Galileo space probe revealed from Jupiter's atmosphere, and then what kinds of particles are in the rings of Jupiter and Saturn, because yes, Jupiter also has rings. They are not as huge and as well formed as the ones in Saturn, but we know that every Jovian planet has a set of rings. And this makes sense based on the size of the planets, based on the large amount of moons, based on the orbits of these rings, right? To explore the rings, we have to use some physics where we use tidal forces to explain why the moons and why the rings orbit at certain locations with respect to the planet, right? So what observations from Earth reveal about Jupiter and Saturn? So we have a table here. Again, you can notice the red dot of Jupiter. You can notice the different bands on the atmospheric surface of the planet. And what are the main properties of this planet? I would say the very low eccentricity. It's very low density, right? It's the most massive planet in the solar system, but it has a very small density. The density of a terrestrial planet is between 4,000 and 5,000 kilograms per meter cube. The average density of Jupiter is about 1,300 kilograms per meter cube. And that's because the composition of Jupiter is mostly, as I said, 71% hydrogen, 24% helium. So that's basically 95% hydrogen and helium gas. It has a huge escape velocity, about 5 times the escape velocity of the Earth, right? The escape velocity of the Earth is about 11.2 kilometers per second. Here is 60, and that's because of the huge mass of the planet, which you can see here. It's about 1.9 times 10 to the 27. That's about 3 orders of magnitude, right? Larger than the mass of the Earth, which is 6 times 10 to the 24, or 5.9 times 10 to the 24 kilograms. So about 317.8 Earth masses. An orbital period of about 12 years. It means that it takes 12 years to orbit the sun, but a rotational period of about 10 hours, 9 hours and 50 minutes. So it rotates very rapidly. And that's going to be important when we talk about the magnetic field that is produced by this planet. And we know it's very large by the auroras, the very large auroras that we can observe from Earth happening on the north and the south pole of this planet. When we look at Saturn, we see that there are some similarities, a very similar rotational period, an orbital period much larger, 29 years. This was 12 years, basically. A mass very high, not as high as Jupiter, but still 5.6, 5.7 times 10 to the 26. So this one will be 2 orders of magnitude larger than the mass of the Earth. So about 95 times the mass of the Earth. An escape velocity of 35 kilometers per second because of the different mass. And well, look at the gravity of this planet, about 9.92. The gravity on the surface of this planet, if anything, if it has a surface, if we can talk about a surface, is twice the gravity of the Earth. The reason is because gravity depends on the mass of the planet and the radius of the planet. It's an inverse square law. The greater the radius, the much lower the gravitational pull, because the equation is basically gm over r squared. So it's an inverse square law. The radius of this planet is about 11.2 times the diameter of the, well, 10 point. The reason you have different diameters here or radius, diameter is double the radius, is because we measure the equatorial and the polar radius and diameter. So there's going to be a difference. However, when we look at that, when we look at Saturn, there is a difference, but not as much as with Jupiter. That is the reason why the escape velocity and the average density is less in this planet, right? This planet is 687, while in Jupiter was 1300. So almost double the density of Jupiter. Or the density of Jupiter is almost double the density of Saturn. And in terms of composition, there is a difference. In the case of Saturn, there is 3.3% helium, while in Jupiter, there is 13.6% helium. So where is that 10% difference? What we think is happening is that helium is raining from the top of the atmosphere as almost like water dropping from the sky towards the surface or even towards the inside of this planet of Saturn. We don't notice, we don't see that happening in Jupiter. So that will explain the difference in abundance of helium between Jupiter and Saturn. These are two pictures to show you how we look at the planets as viewed from the Earth, right? Again, depending where we are, depending on when we are looking at them, sometimes we may see the red spot like this. Sometimes we may not see it because it's at a time where Jupiter is, where the red spot is not pointing towards us. Now, the reason why many pictures have the red spot is simple. The rotational period of Jupiter is about 10 hours. So it doesn't take much time for us to point the telescope at the time where the red spot is in there. So here are a few sections or parts when you're looking at Jupiter. Remember that Jupiter and Saturn both rotate so rapidly, about 10 hours per rotation, that the planets are kind of flattened. What do we mean by flattened? That the polar and the equatorial radius are, the difference is not as much as you will expect from a terrestrial planet. It also has to do with the way it rotates, which we're going to talk in a little bit. Notice the red spot in there, the dark colored belts, the light colored belts, and the shadow of one of the moons. One of the Galilean moons that is orbiting Jupiter, in this case, that one is Europa, right? Remember, these moons were discovered by Galileo in the 1600s. But after that, we have discovered dozens of extra moons orbiting Jupiter and also much more or many more orbiting Saturn. So for Saturn, we have the same. We have light colored belts, dark colored belts, and in this case, the shadow of Mimas. Here it is. These are other moons, by the way, but this one is in between us and the focal point or the focus of the telescope. So that's what we see as a shadow there, the projection on Jupiter, on Saturn. So this is what I was talking about. Solid planets made of rock, like the Earth, Venus, Mars, and Jupiter, they have a solid rotation, meaning that every part of the object takes exactly the same time to complete one rotation. That's the rotation of a solid body. Jupiter and Saturn are not made of rock. They are mostly made of gas. So they don't have a solid rotation. They have differential rotation, which means that particles at different latitudes, they will take different time to complete one rotation. That's because of how the gas, or in this case, the liquid, rotate. Okay, so differential rotation is what we see in Jupiter and Saturn, which will explain the flattening of those planets. In the case of the Earth, it doesn't have that type of situation, right? Because again, the Earth is mostly made of rock. So there you are. Jupiter and Saturn are very rapid rotators. About 9.9 hours, 10 hours for Jupiter, and 10.7 hours for Saturn. So what about the storms that we can see in the clouds of Jupiter? So remember, both Jupiter and Saturn emit more energy than the one they receive from the sun. So what we think is happening there is that the planets are still cooling from the time they were born. Remember, we know that these planets were the ones to form the first in the origins of the solar system. First Jupiter and then Saturn, which basically stopped the planet migration of Jupiter towards the sun. In terms of the atmospheres, right? We notice that the visible surfaces of Jupiter and Saturn are the tops of their clouds, like you see in there. That, for example, is the Pioneer in 1974. So we have sent several missions to these planets, right? The aim of these missions is somehow different. Some of the missions did not just have the objective to explore Jupiter, but also the Galilean moons. Some others were flybys that were orbiting the planet until the mission was accomplished, and then they would crash onto the planet. Some of those, like the Voyager, they just took pictures and then they kept going until they left the solar system, right? The rapid rotation of the planets twists the clouds into dark belts and light zones that are parallel to the equator, as you can see in here, right? The belts are parallel to the equator. Strong zonal winds run along the belts and the zones. The outer layers of both planets' atmospheres show differential rotation. The differential rotation can be noticed when we explore the atmosphere. The equatorial region, however, rotates slightly faster than the polar regions. Not much faster, but slightly faster, as you will expect, as you should expect from having a larger radius. So that's a picture from the Voyager 2, right? Where you can see the dark belt encroaching the red spot, the big red spot there. And this is from the Hubble Space Telescope. This one gives us a few more details that we couldn't notice before, like these white ovals that most likely are other storms, not as strong as the big red dot, but still storms that are forming on top of the clouds. And we see different ovals all over the place here. All right. So what do we notice about the great red spot? We see that winds on the north side of the great red spot flow westward. Winds within the great red spot circulate counterclockwise. All right. Then we can see turbulence happening nearby the red spot. All right. So that's activity that is happening on top of the atmospheres. Right. So the colored ovals visible in the Jovian atmosphere, they always represent gigantic storms. Like the great sun, for example, like the great red spot of Jupiter. And the thing about that, this red spot is that it's very stable and has persisted for hundreds of years, according to documentation. Storms in Saturn, however, they normally seem to be very short-lived, not like the ones that we see in Jupiter. And look at the sizes, right? This is the Earth diameter, about 12,800. So there you are. Okay? That's just to give you a comparison. So when we look at the atmosphere of Jupiter, guys, this is what we start noticing, right? You see that different layers of clouds are about 50 kilometers thick. We see on the top of the layers the gaseous hydrogen. Down there, or at the bottom, between helium and gas hydrogen, we see that liquid hydrogen. But that's just liquid hydrogen. Where the mantle should be surrounding the core, we see liquid metallic hydrogen. That would be the violet, purple, each color here. And then see with a rock ice core. So there are presumed to be 3 cloud layers in the atmospheres of Jupiter and Saturn. The cloud layers in Saturn's atmosphere are spread over a greater range than what we see in Jupiter. Okay? Now, what do we have about Jupiter's interior? Again, Jupiter's interior is mostly hydrogen and helium, gas. The liquid hydrogen, however, it's compressed further until it reaches metallic state. That's what you see here. Liquid hydrogen, and then because of the enormous pressure due to gravity, here is where you start having metallic hydrogen. This occurs at about 20,000 kilometers below the atmosphere. So there's not really a surface, but we can see the different layers of clouds, basically the different layers in the atmosphere of Jupiter. At the very center of Jupiter, about 15 air masses, you see the rocky core. That's where you can find it. So that's what you see from this picture as well, right? Notice the rings here. That's the main ring here that we can see around Jupiter. So how do we divide the layers that we see there? So there you have. Remember the ovals? Those are storms, right? So sometimes we can find brown ovals. Those are north hemisphere storms. And the white ovals are southern hemisphere storms. Okay, you have different zones and bands. You have light colored, dark colored, and you have the red spot in there. So let's see what is the difference. So basically, these zones and belts are considered jet streams, moving at very high velocities. Why do we care about the different types of ovals, the brown and the white? Because they tell you the different direction of the wind. We also see that here on Earth. That's because of the Coriolis acceleration. So in here it says that the light colored zones are regions of upward moving convective currents, while the darker belts are downward sinking material. All right. So that is the difference between the dark and the light or white colored belts. And the boundary between the zones, that's where you find the bands. The zones then are the thicker space in between bands. And as you can see here, you have dark colored bands and white colored bands, just as you have dark spots and light spots. Okay. So exploring the red spot of Jupiter has allowed us to find other red spots. You see that red spot junior? We call it like that because of how close it is from the great red spot of Jupiter, but also because of the composition of the clouds and the wind speed and the direction, which is the same as the great red spot, counterclockwise. So look at this picture here, right? So sometimes these dark belts seem to vanish with a great red spot. We can still see the ovals here, right? This one here, 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 but no great red spot. That's because white colored ammonia ice crystals, they block the darker belt from view. All right. That's another picture there. That will be for Saturn. So on Saturn, the Cassini, a very famous mission that we sent to Saturn, it took different pictures of different locations on Saturn and also observed several storms in different regions of Saturn. This one is basically the exploration of an aurora, where at the same time in 2004, a storm was observed. Okay. So you see the brown and the orange colors here? Well, there it is. The orange and brown colors in both Jupiter and Saturn, by the way, are caused by upwelling. Upwelling is what happens in the ocean, for example, guys. Upwelling is the phenomena of wind pushing away, in the case of the oceans, pushing away the water from the surface, in this case, warm water on the surface, and then letting cool water rise towards the top. So in here, you see the change of color when they are exposed to UV light from the sun. Okay, so this upwelling basically is removing certain compounds, and because of the UV light, you see the change of color. All right, these colorful compounds, known as chromophores, mix with a warmer lower deck of clouds. Okay, and to explain you that better with a graph, take a look at this. So this is the composition of Jupiter's atmosphere. Notice how the temperature increases as you go down, as you go towards the inside of the planet. That makes sense. Temperature and pressure increase, and they give you the different colors there that we also notice here. See that bluish here, brown, kind of white here, red, right? So that's because of the different compounds. You may have ammonia clouds, NH3. You may have water ice or water clouds, ammonia crystals, water droplets, and then molecular hydrogen, metallic hydrogen here. Okay? So that is the reason why you see different colors. Okay? How that happens, as I said, that's still unknown. But we see these colors, and at least we know why those colors are the way they are. Also, remember that we have cyclones, just like on Earth. The difference is the orientation. In the northern hemisphere, they are clockwise. In the southern hemisphere, they are counterclockwise. That's why the great red spot is a counterclockwise cyclone. High pressure cyclone, by the way. So just like on Earth, as I said, cyclones are developed in different directions in the northern and the southern hemisphere because of the Coriolis acceleration that we know as the Coriolis effect, where the lower latitudes travel faster than the higher latitudes. That's why you have those different spinning speeds and different directions. So as it says there, the cyclones on Jupiter are regions of local high or low pressure. All right. So there is another picture there showing you the composition similar to when we studied the composition of the Earth. You have the rocky core, much bigger than the Earth, but very small when we compare it to the rest of the planet. Liquid metallic hydrogen, where the mantle will be. A transition zone between the liquid metallic hydrogen and the molecular hydrogen. And then on top of that, hydrogen and helium gas. The temperature of the core is about 25,000 kelvins, very high, because of gravitational pull or not gravitational pull, gravitational energy. It's kind of what they try to use to explain the energy released by the sun or a star, right? There is a constant pull and decay of material towards the core. And that is what's converted into very large amounts of energy, which you can see by that very high temperature, 25,000 kelvins. Now, the temperature as you go to the top of the clouds decreases to about 300 kelvins. 300 kelvins in Celsius is about 25 degrees Celsius. Pressure at the top is about 0 bars. At the core is about 12 million bars. Okay. And yes, as I said, the shapes of Jupiter and Saturn, the flattened shapes, indicate the sizes of their rocky cores, right? We call that the oblateness of Jupiter and Saturn, okay? So here's another picture showing you the internal structure of both Jupiter and Saturn, right? We talk about both because at the end of the day, composition-wise, they are very alike. And they were formed almost at the same time. Okay. Now, let's explain the magnetic field. Jupiter and Saturn, especially Jupiter, has a strong magnetic field. Why? Just like the Earth, you need currents that are created where? Well, these currents in Jupiter are created in the metallic hydrogen layer, in the purple/pinkish region there. We see evidence of that because of the very large aurora in both planets. You only see aurora due to the interaction of a magnetic field with the solar radiation emitted by the sun, as you saw in that video 2 classes ago. With less liquid metallic hydrogen, Saturn also has a magnetic field, but is weaker than that of Jupiter's. So how do these planets create their magnetic fields? By synchrotron radiation, right? You have charged particles, radio wave interacting, and then in synchrotron radiation, you have a charged particle encountering a magnetic field. This particle is accelerated in a spiral form because you have a magnetic force and an electric force. Then you start having different radio signatures that give us the strength of the magnetic field, because the interaction and the radio waves are due to the synchrotron radiation. All right. And this actually gives us the evidence for the magnetic field, besides the auroras. So pole regions, that's what we see as a bottle or a magnetic mirror, where you trap particles and you can reflect them. And that's where you see the auroras. Okay. Any questions so far about this? So what are the main ideas, right? When you talk about Jupiter and Saturn, the main ideas are to describe the differences between these planets and the terrestrial planets. And you can do that by pointing at different factors like the density, their composition, their atmospheric pressure, their oblateness, and the differential rotation. In the case of in the case of the magnetic field, yes, the Earth also has a magnetic field, but the mechanism is different. We have a magnetic field because the outer core, the molten core, is rotating very rapidly. And by the way, yes, why do we have magnetic or currents in the liquid metallic hydrogen of Jupiter and Saturn? Because of the rapid rotation. The rapid rotation allows the planet to rotate around its axis quicker than any other terrestrial planet. So because of that, we know that a magnetic field can easily be created by this rotation. Okay. So now let's compare and let's talk a little bit about Saturn. So what is the difference between Saturn and Jupiter? We think that Saturn cools faster than Jupiter because it's farther from the sun. So that makes sense. The main difference is that helium is probably raining from the top of the Saturn's atmosphere. So these droplets are condensed into helium rain, just like we see here on Earth, the water cycle. This liquid helium, however, is a superfluid. There's almost no drag, no friction, no viscosity, and can easily go through the hydrogen mantle without any sort of resistance. So we have potential energy from the falling helium converting into kinetic energy, making the core heating up more than Jupiter, for example. So you have a warmer core and you have a lack of helium in the upper atmosphere. This is a very important slide because this shows you the difference between Saturn and Jupiter. which is mainly the absence of helium on the top of the atmosphere, and the fact that because of this, the core of Saturn is warmer than the core of Jupiter. Okay? So what do we see when we look at Saturn from the Earth? We also see the bands of different clouds. And we're going to see why is that. Very similar to Saturn, Jupiter, by the way. It all has to do with the composition of the clouds. What elements you can find, what compounds you can find in the different layers. But the other difference is the rings. And the thing about the rings is that it's not like they've always been there, right? Because of the gravitational pull of Saturn, because of the large amount of objects that are rotating around Saturn, you know, the moons, it's logic to think that just like Saturn, the other terrestrial planets can capture objects that can never drop towards the planet. What do I mean by that? There is an equilibrium between tidal forces and the gravitational pull of the planet that allows the rings to orbit in somehow unstable orbit without being destroyed by gravitational tidal forces between the planet and those moons where they are located. Okay? Stick here. So as you can see, if we compare this picture with the one I showed you before with Jupiter, put it here, right? So there is liquid metallic hydrogen in Saturn, but it's less than what you see in Jupiter. That's because of the helium rain, right? We don't have that in Jupiter. The helium rain basically, besides warming up the core, it also decreases the abundance of liquid metallic hydrogen. You also have helium ices, a rocky core like Jupiter. You still have your hydrogen gas and liquid hydrogen below the atmosphere of Saturn. And also pay attention at the different set of rings and the Cassini division, which is the major division, the major gap between the set of rings in there. Okay? The rings can provide us a lot of insights and information, not just to the composition of the rings and the objects themselves, but also different features of the planet they are orbiting, such as gravitational pull, size, density, etc., etc. And yes, by the way, this is what I wanted to say. I was thinking, how do we know in physics what is the position of these rings, right? What are the allowed orbits for the rings of Saturn, Jupiter, and the other Jovian planets? That's given by the Roche limit. The Roche limit is a physical parameter that allows us to study the limit, no pun intended, for gravitational tidal forces to be in equilibrium with the gravitational pull themselves. That will create a stable orbit for moons to orbit the planet without being decomposed, without being disintegrated by the gravitational pull of the planet. It's not the same as the orbit of the moons. The moons are at a greater distance. So for the moons, just like our moon, we only need a gravitational pull, a gravitational force. In here, we have to look at tidal forces. What are tidal forces, by the way? Well, I'm going to assume that many of you have seen or have read about black holes. So you probably have heard about the spaghettization effect, and you probably have heard about the accretion disk surrounding the event horizon of a black hole. So you should know that if the sun became a black hole, the Earth will keep orbiting the way it does. It just will freeze because there's no more heat. So it's not that the black hole is sucking everything. It only does that when an object approaches the black hole that is going to go within the event horizon of the black hole. So on the limit of the event horizon and the accretion disk, that's when tidal forces become so strong that, for example, the matter of a star is disintegrating into gas that is eventually sucked into the black hole. So tidal forces, guys, are forces exerted by massive objects in the universe, breaking planets, stars, or asteroids and comets apart. This can be explored as well when you look at what happened with a Shoemaker-Levy, a comet that crashed onto the surface of Jupiter. This comet, as it approached Jupiter, by the tidal forces of Jupiter, it broke into different parts before it crashed onto Jupiter. Another one will be the Hayakutake comet that I remember very well. I was a kid, very small kid back then, but people were scared that it could actually crash onto the planet. But it didn't happen, and it went actually on its orbit around the sun. And what happened is when it was approaching the sun, because of the enormous gravitational forces and tidal forces, it started to disintegrate. So those are tidal forces, and moon, in this case, rings, they survive that because of the rocket. All right? So here's a comparison between Jupiter and Saturn. Obviously, Jupiter is much bigger, but very similar, right? We still have a rocky core, a metallic hydrogen mantle, orbiting or rotating very rapidly because the planets rotate very rapidly. Molecular hydrogen was missing in the case of Jupiter, is missing the helium ray, helium droplets in between the liquid metallic hydrogen and the molecular hydrogen. All right. That's what's missing between these two. All right. So in here, they just give you a few main parameters, such as the fact that Saturn's features are because the atmosphere is thicker. What they mean by that is that the gas section of the atmosphere is thicker, right? Jupiter has a greater mass, so has a greater gravitational pull. All right. And then that's basically it. I mean, obviously, more mass, more gravitational pull. All right. You probably have heard about the rings of Saturn disappearing from eyesight of our planet. That's just because of how Saturn orbits the sun and our position respect to the sun and Saturn. Sometimes we can see the top of the ring, sometimes we can see edge on, sometimes we can see them underside, sometimes they are barely visible. Because if we are between, if we are in conjunction, which means that the sun is in between us and Saturn, chances are that the rings of Saturn will be blinded by the light of the sun, and we wouldn't be able to see them, right? So it's not like the rings disappear. It's just that it depends from our point of view, from our perspective. Okay. Now, I did mention that every planet has rings. This is an important slide. Take a look at this. All the 4 Jovian planets, have rings. And we have characterized the different sections of these rings. Saturn has 3 major broad rings, A, B, and C, that can be seen from the Earth. Other fainter rings were found first by the Voyager spacecrafts. All right. Each of Saturn's major rings is composed of great many narrow ringlets. For example, faint F here, right, which is outside the A ring, is kept narrow by the gravitational pull of Saturn and the other satellites. We see different divisions between the rings, between the sections of the rings. That's because of gravitational pull between the planets and the satellites, the moons of Saturn, right? Titan, Enceladus, etc., etc. And as I said there, the rocket limit is what gives us the position of the rings. A planet's rocket limit is about 2.4 times the radius of the planet. For denser material, the rocket limit is closer to the planet. So for example, for us, for the Earth, the rocket limit is closer to the orbit of the Earth. All right. So you can see the rocket limit in there, right? Jupiter faint rings are composed of relatively small, dark, rocky particles and ice. Most of the rings are made of rocky particles, ice, and in some cases, apparently diamonds, compound diamonds that are ejected from the atmosphere of the planets. Or sometimes ejected by the moons, like you're gonna see in a bit. Io ejects a lot of material because it's the most volcanic object in the solar system. So that material can be grabbed by the gravitational pull of Jupiter and can eventually change the composition of the rings. All right. So rings are very thin compared to their width. Look at that. Again, this is due to the fact because of the orbit where they are. All right. Also, there are collisions in the rings, which will cause some of the particles to exchange energy, some of them to combine, some of them to basically disintegrate. All right. It depends on the speed of how they are orbiting it. And this is a better picture, right? You can see the Cassini division, which is the major division of Saturn rings, and you can see the other fainter rings. Think about the fainter rings as the rings that you can see in Jupiter, Neptune, and Uranus, right? They don't have broad sections of rings like Saturn has. They have the fainter ones, not the broad ones like Saturn. All right. So that's basically the major thing, guys. These with the videos that we have watched before about Jupiter, the exploration mostly, right, of Jupiter. This gives you a good amount of information of both of these planets, right? I always tell students that the idea of exploring the Jovian planets is to highlight the difference between the composition of those planets, the physics behind those planets, and what we're going to talk about now, which are the moons and the terrestrial planets, right? The composition is very different. The densities are very different. The rotational period and the way they rotate is very different, right? So keep that in mind when you are being asked this in the exams, right? In the exam and also the final, right? Things that you can be asked are to compare the for example, to do a general comparison between the atmospherical characteristics of Jupiter and Saturn, because they're very similar, to that of Earth, Venus, and Mars, right? I know they are different, but there are some similarities, right? In terms of the thickness of the atmosphere, in terms of the oxygen abundance in the Earth, and the carbon dioxide abundance in Mars and Venus. The greenhouse effect that happens in Earth and of course in Venus, and the composition and the composition and the thickness of the atmospheric gas of Jupiter and Saturn, right? The other thing that you should also always take into consideration is that these planets, besides rings, have a huge amount of moons. When we talk about the moon of the Earth, I said that it's very odd for a planet like the Earth, first of all, to have a moon, and second of all, to have a moon the size of our moon, right? When we look at the moons of Jupiter, for example, the 4 Galilean moons, we notice that they are the 4 largest moons of the solar system. But in the top 5, we can include our moon. That's what makes it odd. In the case of Jupiter, it's not odd because Jupiter is a very large planet with a very large gravitational pull, where it makes sense, just like planets were formed around the sun, it makes sense for rocky and icy material to accrete into spherical objects that ended up being the moons of Jupiter and of course as well the moons of Saturn, right? So what are the main differences between these moons and the hosting planet, for example? The density, right? In there is grams per centimeter cube. The density of Jupiter is about 1.3 grams per centimeter cube. When you want to convert, when you convert grams per centimeter cube to kilograms per meter cube, you multiply by 1,000. All right? So that's why you have that. So it's much more dense because of their composition, except maybe Ganymede and Callisto. In terms of the radius, I mean, they are kind of comparable, right? Their orbital periods. We have found that there is sort of a relationship between the period here, 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 and here. Look at this. If you multiply 1.77 times 2, I get exactly 3.5, well, basically 3.55. So the period of Europa and Io are in relation of 1 to 2. And what happens if I divide? I get exactly 4. So this is like 1, this is like 2, this is like 4. And look at the, with Callisto, it's not exactly, I believe. Yeah, it's 2.3. So if it was 2, then you can say this is like 1, like 2, like 4, like 8, right? But at least with Io, Europa, and Ganymede, there is this kind of gravitational synchronization of their periods. And that is actually not weird. Why? Because we see with the moon, the gravitational synchronization between the orbit of the moon as it orbits the Earth. But also because these Galilean moons are the largest and are the ones that are relatively closer from each other. If you go to Stellarium right now or after class, you click on Jupiter and you zoom in, you can easily spot the Galilean moons. If you fast forward time, you can start easily seeing how there is sort of like a carousel that you're going to start seeing among the 4 moons of Jupiter. The 2 innermost Galilean satellites, Io and Europa, have about the same size and density, as you can see from the table. They are mostly made of rocky material, as you can see from the density. The outermost, Ganymede and Callisto, are roughly the same size as Mercury. So look at the size, right? Lower in density because they are made of equal parts of rock and ice. And ice has a lower density, so that makes sense. We think that at least the Galilean moons were formed similarly to our solar system, but in a smaller scale. That's what I was talking about. Jupiter is big, so it was able to form by accreting material. Like planetesimals accreting to form planets around the sun. So nothing weird there so far, right? By the way, remember that this was used as evidence. Galileo used this as evidence to corroborate the Copernican model. When we talk about that in chapter 4, right? That the sun is at the center of the solar system. Okay, so what do we see about Callisto? So with Callisto, we see a dark surface. It's one of the largest and most heavily cratered satellites in the solar system. The surface is basically mostly ice. And beneath this ice, maybe, we think there might be a very salty ocean supported by a very rocky interior. Callisto doesn't have any mountains. It does show some evidence of tectonic and volcanic activity. However, observations of Callisto's magnetic field, right, has given reason to believe that there may be a subsurface salty ocean. And as it says there, right, roughly 10 kilometers thick, about 100 kilometers below the icy surface. All right. So that's Callisto for you. What about Ganymede? So the surface of Ganymede and Europa are very similar. You start seeing those channels. You start seeing craters as well. But you also see water ice. But unlike Europa's surface, it does show varying age. The darker regions are heavily cratered, yes. And the lighter regions of Ganymede show no signs of craters. And it's believed that they are due to eruptions of water covered by the surface before it froze over. If liquid water occasionally made its way through the surface, filling the craters, it suggests that there may be an ocean similar maybe to what we expect to find beneath the heavy ice of Europa. All right. That brings us to this. Well, before that, let's take a look at the influence of Jupiter and its moons, right? You see that heavy elliptical orbit there. So what can we say about Europa? Very interesting moon. So Europa is primarily made of rock, but is covered by a smooth layer of water ice. What we think is happening in Europa and also in Io is tidal heating. All right. So this tidal heating is a very important source of energy below the ice within the theoretical, not theoretical at this point, but beneath the ocean of water. The icy surface is nearly devoid of impact craters, and it might just be a few million years old. All right. The tidal heating is basically due to the gravitational pull between Jupiter and the moon itself. All right. This ocean beneath the Europa's frozen surface may have many minerals that have been dissolved in this ocean, which explains the induced magnetic field that Europa has, because that's where the currents come from. All right. The stretching and squeezing of the tidal friction between Europa and Jupiter, Jupiter, it provides enough heat to melt some of the ice. So that's why we think there is liquid water beneath the icy shell. This water then will allow us to find an ocean that may have twice much as liquid water as all of Earth's oceans combined. When we look at close-up pictures of Europa, it does support the idea of liquid ocean beneath the surface. Most of these pictures were taken by the Galileo spacecraft, by the way. And what they show what appears to be icebergs stuck in the layer of ice. Other evidence comes from rich cracks on the surface. This is due to tidal flexing that allows water to well up and build ridges, basically to create perturbations in the ice. I'm talking about these guys. All right. Later on, just like in Enceladus, we have discovered plummets, right? Sort of like water ejecting from the surface. For Enceladus, for sure. So that's a strong evidence that there is most likely water underneath that icy shell. And if there is water, most likely with a tidal heating, there is a perfect environment for organic life to be existing in that moon, right? That's why I said, I believe I said this at some point in class, at the beginning, that a very important, more than the planets, Mars or even Venus, the moons, such as Ganymede, Europa, Enceladus, Titan, are more interesting objects to look for evidence of organic or maybe inorganic. All right. What about Io? So the Voyager spacecraft is the one that took the first close-up images of Io. These images show a surface with no signs of craters from past impacts. Why? Because what they saw is an entirely surface covered by large volcanoes. The cameras of the Voyager actually capture volcanic eruptions in progress. For example, look at this. That one there. The frequency of these sulfuric eruptions has filling almost all the impact craters. That's why you don't see them. Close-up photos of eruptions in progress show hot lava glowing. You can see here. Orange and red. All of this. Debris ejected from different volcanic activity. All right. However, Io's unusual red and orange color, they come primarily from sulfur, all right, which condenses on the surface after being outgassed by volcanoes, all right. Now, there is no evidence of tectonic activity on Io. However, there is the belief that processes that fuel volcanism may also fuel tectonic activity on the surface. The volcanic eruptions are so frequent and cover the surface of Io so thoroughly that any clear evidence of tectonic activity is likely to be hidden under that volcanic activity. All right. So what I want you guys to get about this? That even though there are many moons orbiting these planets, right? It's very interesting to explore these particular moons because of the possibilities of geological activity, life, liquid water, or ice to be found in some of these moons, which will leave them as a perfect candidates for life to evolve or to at least exist in some way or form in those planets, in those moons. So now I can show you this small summary. Oh, what is this? Okay. There. This will summarize the moons. Okay. There you are.
Amazing Moons, presented by Science at NASA. When the space age began more than 50 years ago, explorers were eager to visit the planets of the solar system. As the years have passed, however, astronomers have realized that the moons of the solar system may be even more interesting. Many of these moons are water worlds, and planetary scientists, like golden retrievers, always follow the water. On Earth where there is water, there is life, says Brian Day of NASA's Solar System Exploration Research Virtual Institute. It doesn't matter if it's boiling hot like the bubbling acid hot springs in Yellowstone National Park, or frigid like the waters of the Arctic. Consider Enceladus, a tiny moon floating just outside Saturn's rings. This little wonderland features a vast underground ocean that could be friendly to microbial life. That ocean is capped by a thick crust of ice. Yet, NASA's Cassini spacecraft found Enceladus busily puffing plumes of water vapor, icy particles, and organic compounds out through fissures in its frozen outer shell. Cassini has actually flown through these plumes a few times, sniffing out their composition. Day says, the exciting results from Cassini have researchers designing possible future missions that would provide more detailed analyses of Enceladus's water and look for potential signatures of life. Titan, another of Saturn's moons, is shrouded in a thick atmosphere of nitrogen and methane. There is evidence that Titan, like Enceladus, has a sea of water beneath its icy shell. But Titan's frigid surface is mosaicked with lakes of liquid methane and ethane. Day notes, it's the only body in the solar system other than Earth with substantial liquid on its surface. The seas of Titan intrigue astrobiologists. Here on Earth, our seas are teeming with life, and indeed the seas may be where life began. What kind of life might arise in the alien seas of Titan? The exotic environment of hydrocarbon seas could teach astrobiologists a lot about the basic chemistry critical to the formation of life. More water worlds with icy shells are found at Jupiter. Europa, Ganymede, and perhaps Callisto also show strong evidence of liquid water oceans beneath their global ice crusts. Day would most like to dive in at Europa. This is a big world, much bigger than Enceladus, and even bigger than any of the dwarf planets. Europa's ocean is a significant body of water with amazing potential for life. In fact, Europa has twice as much liquid water as Earth, and like the water of Enceladus, it might be accessible. There is some evidence that Europa may have periodic eruptions of plumes of water, similar to those seen on Enceladus. We've even seen apparent icebergs on the surface that are tipped up as if sitting in slush. All of these provide us with tantalizing clues of what lies beneath, an ocean of liquid water. Meanwhile, orbiting Jupiter not far from Europa is a completely different kind of satellite. Io, says Day, is the most volcanically active body in our solar system. Io gets its fiery warmth from tidal heating, that is, a back-and-forth stretching of the moon's interior caused by Jupiter's intense gravity. Each moon is stretched and pulled differently, causing varying rates of tidal heating. Orbiting more closely to Jupiter than the other Galilean moons, Io is stretched the most, hence its volcanism. Europa, next closest to Jupiter, is stretched less, followed in order by Ganymede and Callisto. Day continues, saying, tidal heating is a source of energy that can melt ice and expand the potential for life. It creates a habitable zone among the moons of Jupiter, with Europa sitting squarely in the middle. Planets are exciting, but there's an even greater number of amazing moons in the solar system. Says Day, the lure is irresistible and the potential is amazing. It's time for us to go. For more news about amazing moons and their planets, stay tuned.
All right, guys. So that's nice for you to summarize what we spoke today about the moons. Okay. All right, guys. So that's almost it, right? We have just two more things to discuss: the Neptune and Uranus, and comets and asteroids. This is very short, by the way. So what I'm gonna do is I'm gonna post a quiz, the last quiz, next class, but we're gonna do it at the end. So next class, we talk about Neptune, Uranus, and then I'll open a quiz so you guys can submit it. It's gonna be like an online quiz, all right? So you don't have to be in class to take it. And then that's it, all right? As I said, we have our last class the 10th of December and the final exam the 12th of December, right? Exam free will be December 5th. All right. Any questions, guys, before we finish today?
Do we have class on Thursday?
This Thursday? Yes, we have the last lab this Thursday.
All right.
All right. So I'll see you guys on Thursday. Make sure you submit the assignments that I'm already posting, and yeah, just get ready for what's coming next. Have a good night.